Hi, today we try to solve the Legendre differential equation and obtain a solution of the Legendre equation. As we all know, the Legendre equation that is given by 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 y equal to 0. So this is the Legendre differential equation. Since we have minus 2x here, we can write this in this way also. D by dx of 1 minus x square dy by dx plus n into n plus 1 y equal to 0. Okay, so this is the Legendre equation. And we are using Frobenius method for solving or for obtaining a solution of the Legendre equation. And this Legendre equation can be solved in series of ascending or descending powers of x. We solved the simple harmonic oscillator problem, the Bessel equation, in the ascending powers of x. Okay, the Legendre equation we are solving in descending powers of x because the solution in descending powers of x is of more physical importance. Okay, the solution that we obtain when in series of descending powers of x is of more practical importance than the ascending powers of x. So we consider the solution in descending powers of x, and we write it as y equal to sigma r equal to 0 to infinity ar x to the power k minus r. Okay, so r is varying from 0 to infinity, so we have descending power of x. Then dy by dx, that is given by sigma r ar k minus r x to the power k minus r minus 1. And d square y by dx square is sigma r ar k minus r minus 1 x to the power k minus r minus 2. Okay, so this is y. Then here we find dy by dx, and then we find d square y by dx square. We substitute all these things in this equation. Okay, here we substitute. As we substitute, we will be getting this 1 minus x square sigma r ar k minus r minus 1 x to the power k minus r minus 2 minus 2x sigma r ar k minus r x to the power k minus r minus 1 n into n plus 1 sigma r x to the power k minus r, that is equal to 0. So we substitute for y dy by dx and d square y by dx square in the equation 1 here. Okay, here. Now we have this substitution, and we write like terms together, the coefficient of x to the power k minus r minus 2, that is written here. The second term is the coefficient of x to the power k minus r, so they are brought together. So we write the coefficient of x to the power k minus r minus 2 and k minus r like this, and we write it in finally in this form. It is written finally in this form. Okay. So the coefficient of the highest power of k, that is x the power k, the coefficient of the highest power. See, here we are taking the highest power of k, highest power of x. Okay, that is obtained by putting r equal to 0, and that is when you put r equal to 0 here, you will have x the power k. This is the coefficient, this coefficient. Here we have x the power k minus r. We put r equal to 0. So x the power k, and it is given by this. N into n plus 1 minus k minus r. K minus r plus 1, a naught equal to 0. A naught is not equal to 0. So this part has to be 0. So we have this n into n plus 1 minus k into k plus 1 equal to 0. N square plus n minus k square minus k. And we will get n minus k n into n plus k plus 1 equal to 0. And this is the integral equation. And k, the value of k, the root is n, or k is equal to minus n plus 1. So these are the roots of the equation. Okay. So these are the roots. And the next we see the coefficient of x to the power k minus 1. Okay. Coefficient of x to the power k minus 1. And we put r equal to 1 in this equation here. For r equal to 1, we put so we have this the coefficient of x to the power k minus 1 when we put r equal to 1, and we get this equation, and finally we get this. And when k is n or k is minus n plus 1, the roots k equal to n or k equal to minus n plus 1, this cannot be 0. This part is not equal to 0. So a1 must be 0. So a1 is 0. Okay. So we get this a1 equal to 0. And the coefficient of the x to the power k minus j. We are taking the coefficient of x to the power k minus j. This is for determining various coefficients, various a values. So the coefficient of x to the power k minus j is taken. So this is obtained by putting r minus 2 equal to r plus 2. Here we have k minus r minus 2. Okay, k minus r minus 2. So r plus 2 is put equal to here we have x to the power k minus r minus 2. Okay, x to the power k minus r minus 2. So we put r plus 2 equal to j, so that we get the coefficient of x to the power k minus j. and here we put x equal k equal to r equal to j to get the coefficient of x to the power k minus j. Okay, so we have from the first term we will get this. We put j equal to r plus 2, so we get this. So r will be j minus 2. So for r we are substituting this, and when in the second term when we put r equal to j, we get this, and from that we can obtain this aj. Okay, we keep aj on the left hand side and take aj minus 2 and these terms to the other side. So we get aj equal to this. Aj equal to minus k minus j plus 2, k minus j plus 1 over n into n plus 1 minus k minus j plus 1 aj minus 2. So we have got a relation to determine various values of a. Okay. So when k equal to n, we have aj equal to this. Okay. aj equal to minus here we put k equal to n. So as we put k equal to n, here we put k equal to n. Okay, k is n. So we get this, and we will obtain this relation. aj will be aj equal to this minus of this n minus j plus 2 into n minus j plus 1 over j 2n minus j plus 1 aj minus 2. So this is what we get. Okay, now here if I put j equal to 2, I will get a2 in terms of a0, and if I put j equal to 3, I will get a3 in terms of a1. Okay, a1 is 0, you know a1 is 0. So we have this as so when we put j equal to 2, 3, 4, etc., we have a2, a3, a1 0, so a3 0, a5 0, a7 0. So all these coefficients are 0, and a1 is this. Sorry, a2 is this. A2 is this in terms of a0. So a4 is given by this. Here for a2 we substitute this, so we have a4 in terms of a0. So this is a4 in terms of a0. Okay, in this way we can find, if we continue to do this, we can find a6, a8, etc. Okay, then we assume the solution y equal to this. Okay, we put k equal to n. This is the first case, k equal to n. So as we substitute, we have this. As we expand and give values for a0, a2, a4, etc., we have this expression. So this is the series corresponding to one solution of the Legendre equation. Now here for this a0, if I put this, for this a0, if I put this 1 into 3 into 5 into 2n minus 1 over n factorial, Then the above solution is called the Legendre polynomial. It is called the Legendre polynomial or Legendre function of the first kind Pn of x. So if this a0 is this, then this is called the Legendre function of the first kind Pn of x. Okay, so this will be the Pn of x. Pn of x is this. Okay, this is Pn of x. 1 into 3 into 5 into 2n minus 1 over n factorial. This series, this is the Pn of x, the Legendre function of the first kind. Now in the next case, what we see is the k equal to minus n plus 1. This is the next case that we see. And in the expression for aj, we put k equal to minus n plus 1, and we will get this. Once again, a3, a5, a7, these are all zeros because a1 is 0. Okay, so all these are 0, and a2, we are going to get this. Okay, in terms of a0, a2 is this, and in terms of a0, a4 will be this. Okay, that you can find as we did in the previous case for k equal to n. And if I substitute all these things here in this general equation, we know k is minus n plus 1. We are considering this second case now, k equal to minus n plus 1. So we put k equal to minus n plus 1 here. And we have this series. If we substitute for a0, a2, a4, etc., we will get this expression. So we get a series again. And once again, if we are taking a0 as this, we have a0 in each of these terms. That's why it is taken as a common factor. And if that a0 is n factorial over 1 into 3 into 5 into 2n plus 1, the above solution is called the Legendre polynomial or Legendre function of second kind, denoted by Qn of x. Okay, Legendre function of the second kind, denoted by Qnx. So we have seen the series solution of the Legendre equation. We get two solutions, Pn of x and Qn of x. Okay, the Legendre function of the first kind and the second kind.